Thank you very much. It's an honor. It's a very great honor. Thank you for being here. Yeah, I forgot the title on the title slide, but it's supposed to the one thing.
You're forgiven.
Rookie mistake.
We're here to learn.
Rookie mistake.
I'd like to acknowledge the people indicated on this slide who are on the steering committee or who contributed to founding or helping to support the MPP program. I haven't heard the steering committee members thanked, and I would like to thank you myself. Also Lisa Beasley, who actually helps anything to happen, and frequent participants in meetings and who have engaged with MPP students, including Alex Spirits, actually, who's almost everywhere all the time. So thank you. Thank all of you. Thanks to all of you. All right. Also tonight, committee members, three of whom are here today in person. Gila Scher, Eric Breck, Marco Panza, Drew Bocher, contrary to alphabetical order. All right, so my text, the one I'm going to be focusing on today, is an article by Hannes Leitgeb, with whom I've corresponded a bit. Any misrepresentations or misunderstandings, of course, are entirely my own. He's helped me to understand his argument some. I'll do my best to reconstruct it my own terms. And as I understand what Dr. Leitgeb is trying to do, is to help explain what most people take to be a feature of mathematics, the truths of mathematics, which is their necessity, their necessary truth. There's not a lot of this going on in the literature, so there's some room for me, I hope, to add in this presentation a few small things, but mostly I'll be trying to explain what Dr. Leitgeb did. But he and I are both trying to understand if mathematics is necessary, why is that so? So my plan for the talk is as follows. I'm going to, as best I can, after giving a little background, reconstruct the derivation that he offers by way of explanation of the necessity of mathematics. The key feature is that where he wants to get necessity from is standard set theory, Zermel, Frankel. Choice may not come into it, but let's just say ZFC. And there is some philosophy that goes on there and maybe a few minor technical things. And if possible, I'd like to strengthen what Leitgeb does as much as possible and, as Marco put it, minimize the cost of what he's selling, because I would like to buy, but we'll see if there's sufficient funds.
So if I understand well, I come back. The first part, you reconstruct like the argument, and so your contribution here to make the argument clearer.
I hope.
And then your contribution in the last part to try to modify the argument in such a way to make it less costly.
And to spell out the sort of the key feature, what I take to be the key feature of the argument in a little more detail than Dr. Leitgeb does in a very efficient 10 pages. So I don't hold it against him, but I'd like to be of assistance.
Ben, I know that you are still a student, but now at this moment you're speaking as a scholar.
Yeah.
A scholar say Dr. Leitgeb.
How should Leitgeb?
Hannes Leitgeb. The fact that he's a doctor is all totally irrelevant. What is relevant is what you do.
The wonderful man and scholar.
Don't tell him,
Hannes
because then he's not going to get a doctorate.
Oh, because
Whatever it's
it's Dr. Leitgeb.
Sorry?
Yeah, yes.
Now, okay, what do you mean less costly?
Professor.
Which
This is part of the discussion. This will be part of what you
Number of assumptions one has to take, sacrifices one has, trade-offs one has to make in one's views.
Thank
you. I hope it'll be clear eventually. So I need to do a little background and motivation, and this, I admit the philosophers may get a little bored. I'll ask your patience and forgiveness. Then I'm going to say what are the key assumptions, because the derivation is a derivation. It's going to be symbolic in K, in system K. So it's not going to be really user-friendly. Then I'm going to spell out what I take to be the key move is where does the necessity come from? We're trying to derive and thereby explain the necessity of mathematics. Well, where do you get the necessity? I'm going to try to show and lower the costs of getting it, perhaps, or at least make it clear what the cost is. How can you decide whether or not to buy if you don't know what the cost is? And then at the end, we perhaps for discussion, we can talk about, well, what are some alternatives? Who's willing to buy? We can have an auction. So the background, I am going to ask the patience of the philosophers, but sometimes philosophical questions are a little hard to digest for non-philosophers or even for philosophers. And this example is chosen for a purpose, though, for this presentation. It's not a random philosophical question. In the Euthyphro, Socrates got into a dialogue, as he tended to do. And what is piety or holiness? What is it to be holy? Well, one can offer the following definition, and one can even strengthen it to say, of necessity, any X you consider, is this holy or not? It's holy if and only if it is loved by the gods. In Greece, they were polytheistic. Or one can say, is something holy if it satisfies the commandments. But philosophers are never satisfied. You would think a necessary or a strict definition would be good enough. Socrates looked for definitions. But then he said, no, I'm still not satisfied. Find something that's holy and loved by the gods, and therefore positively, affirmatively satisfies the by condition. Is it holy because the gods love it, or do the gods love it because it's holy? What's the order of explanation? Is it commanded because it is holy, or is it holy because we are commanded? To put it in other words. The biconditional doesn't tell us it's symmetrical. It's a symmetrical operation. But explanation we usually do not take to be symmetrical. So we're going to come back to this one and see a little bit more about what philosophical questions often entail when we get to asking questions about a subject area other than piety or justice or whatever Socrates was interested in. We often ask, well, what are some defining characteristics of, let's say, a field of knowledge, area of inquiry? Why does it have these characteristics? So you may have gathered this is a talk in the philosophy of mathematics. So some questions you can ask about mathematics, assuming it's true and we have knowledge of mathematical truths, somehow we know some things. Well, how does that happen? Many people believe we don't do experiments to learn that 2 + 2 = 4. We go through 100-some pages of Principia Mathematica. We prove, we reflect, we think, we write out a proof. Not a full proof, because I guess it would take millions of lines, without exception in Principia Mathematica. Another question you can ask is, well, most people take the truths of mathematics to be necessarily true. They wouldn't change if the world changed in other ways, although I'll say a little bit more about that. Okay. So to say a little bit more about necessity, because this could mean a number of different things. There's a tradition of talking about modalities of truth. We can ask whether something is true or not, but we could also ask sort of in what way is it true? Is something necessarily true, or is it just plain true? Is it possibly true? So you're going to see this operator, the box, which is now used in symbolic logic to represent necessity or sometimes other modalities. Another way to think about this necessarily true is it's always true, true without exception. There's a certain kind of variation. Well, let's look at some examples. So in logic, you do a truth table, you get a column with all T's in it. Well, that's a tautology. That's an example of a logically necessary truth. A contradiction is another kind of necessity, is necessary falsehood. We think those are described impossible situations. They could not possibly, contradiction could not possibly be true. There's another kind of necessity which philosophers tend to truck in, which is metaphysical necessity. So we often take as a base sort of the logical truths, propositional and first order, and then we add this truths that we get out of true identity statements. A famous example is water is H2O. So it's really the sum total of what it is to be water, let's say some quantity of water, even down to a single molecule, is that it's H2O, 2 hydrogens and oxygen arranged in a certain pattern. And that this is necessary for reasons we'll get into in a bit. Philosophers take this to be perhaps almost strongly necessary as a tautology. But one little worry or question you could have about metaphysical necessity is, well, why do we know water exists? We know H2O exists. We know that there are true identity statements about them. But what about a squared circle? Well, is that, what can we say about that? Identity statements involving the square circle. Well, we'll see if that plays a role eventually. One thing to note before we get into the derivation is that without going through a whole review of modal logic, one thing to bear in mind is this box behaves sort of like a universal quantifier. If you want to think of it if that helps you, you can think of it that way. But in terms of its interpretation, philosophers often talk about possible worlds. So a very brief background on what a possible world is. The SEP article says, and I added consistent, a maximally inclusive situation. So if you imagine the situation in this room, very pleasant situation, great place to begin. You go to the campus and then to Orange, and then you keep going and going and going. Eventually you reach a limit of that expanding the situation, and that's the actual world. And that's an example of a possible world. You can't expand the situation anymore, you reach the edge in some sense. So if a statement A is necessarily true at all possible worlds, will you take this world and every other possible world? And the statement is true in all those worlds. Now you could immediately see an obstacle for asking about the necessity of mathematics, which is, what about worlds where there are no people thinking, no people doing math? So what I think I want to aim for is that if we visited a world in a spaceship, say, a trans-world spaceship, we could do math while we stayed in the spaceship, even in a world with no objects or with no everything was at absolute zero or whatever strange situation you want to imagine. So I think one way to put what Leitgeb is going to do is to say, well, I'm going to find some feature that applies to statements of mathematics that we are going to derive the necessity, but we're going to kind of find a feature that they all have in common or that we can attribute to them. And then this feature is going to help us explain why is it that you could do math that not only do math, but get the same math, the same theorems of math in any world. Why would the theorems of math stay the same if you went to a radically different situation? So the details of that. Just to say a word about my motivation for investigating necessity, it's commonly believed, but perhaps not commonly understood or very well understood, why the truths of mathematics are necessarily true. So it'd be nice to know that, and I think there's a kind of uniformity or even elegance or beauty that it adds to mathematics. All the theorems in some sense are on a certain plane. To give you a slightly more concrete example of perhaps a material benefit, or for mathematicians and philosophers a material benefit, I'm borrowing from a talk a couple weeks ago that Wes Holliday gave, and he very kindly shared this slide with me. And so in this derivation, the details don't really matter, but if you're dealing with a contingent statement P, we showed how the rule of reiteration, those who are here will recall, can get you in combination with something called what he calls Wittgenstein's law, can basically lead to explosion. And at lunch, I was about to say Dr. Holliday Wes, as he prefers to be called, pointed out, well, this situation couldn't arise for if mathematics is necessarily true, because the key move here is to get not P and possibly P, which you cannot have for necessarily true statements. So the details don't really matter, but this is a little proof of how that works. Basically, the problematic line is blocked if you're doing reasoning within mathematics, and you can take for granted that math is necessarily true. You can't get a situation like that.
So sorry.
Yeah.
It's not clear. What is the problem here?
Yeah, so from line 8, line 9, the right disjunct is, according to Wittgenstein's law in this Wes's system of epistemic logic, this is necessarily false. It leads to absurdity.
Okay.
And so by
It's
disjunction,
getting P from just possibly P.
Yeah, that's right.
And that shouldn't, possibly P isn't sufficient.
It's not sufficient for P. Yeah, that's very well put. That's right. So it's at least very close to deriving an arbitrary statement. It's very close to explosion. So that's very my gratitude to Wes for sharing this slide. And why do I want to focus on an article with derivation? Because I think arguments can be explanatory. And here's one example. You have a flagpole, you have a sun at a certain angle, you get a certain length of shadow. This is, now I omitted the trigonometric details, but if you put those in, it turns out to be a valid deduction. It's a sound deduction, given the details of the example. And in the philosophy of science, it's often, if these sound deductive argument is taken to be capable of explaining a phenomenon. I think Hannes Leitgeb has something similar in mind. All right. We're going to need some ingredients. So not surprisingly, we're going to have something about math and something about the source of the necessity. Where's this necessity of math going to come from? There's an initial worry you could have, which I think also Leitgeb had in mind, which is if you try to find the source of the necessity within mathematics, you risk a circular explanation. Mathematics is kind of explaining something about itself. I'm not saying that what is necessarily caught in this dilemma, but it's something to bear in mind. Whereas if you have an external source, well then, how do we know that this external source is appropriate since the content of mathematics is sort of specialized? Yeah, Dominic.
Right, so here, what specifically do you mean by mathematics? You mean ZFC?
ZFC, group theory, algebra, whatever you want, we could probably negotiate, but what's commonly taken to be mathematics.
Anything formalizable in ZFC.
Yeah, that's what I thought. Anything formalizable in ZFC, yeah.
Yes. Yeah, that's what we're going to get. You anticipated the next slide, or the next two slides. So I think what Leitgeb is trying to do is to basically split the difference, because ZFC is a part of math. That may have been one of the motivations for your question is, well, isn't ZFC math? But it's sort of taken to be a special branch of mathematics, a foundational one. So hopefully we're sort of threading the needle here between the two horns of this dilemma. That's the hope. And so I think some of the benefits are that perhaps we can get past that dilemma. We can find an explanation for the necessity of math. And ZFC, it turns out, might be negotiable. We might not have to use ZFC, although that's what I'm going to do for the purposes of explicating Leitgeb's argument. A little more background, I apologize, a lot of background here. You'll thank me when we get to the derivation. Yeah.
Can I just go back? Just to make sure, swap in another source. This doesn't seem so innocent to me. Potentially, if that is possible at all, couldn't that endanger the whole argument?
Well, that's a very good question. But if there is, let's say there's another branch of mathematics which turns out could be foundational, then possibly we could use that instead of ZFC.
And then the necessity would come from any foundation.
Well, if it has certain features which Leitgeb claims that ZFC has.
Okay.
Yeah. Which I know I'm putting off a lot, so I appreciate your patience.
But by the way, this feature will be implicitly clear by the argument itself. So you can take any other foundational theorem that can
I have to wait for that.
satisfy the premise in the argument that satisfies, so you can replace it. The problem is, according to me, that if I does not satisfy its premise, but this is another story.
I'll try. We'll see. The one technical detail is that we're going to use the system K, which is a minimal modal logic. And these are the characteristic rule and axiom, but really it's the distribution of the box which is going to play a role. So this move is legitimate. But according to Kay, named for Kripke, no less. So before setting it out formally, here are these assumptions. We're just going to assume that the truths of mathematics are what's commonly taken to be true in mathematics. We're not going to fight over that. Not today. We're just going to grant that without any support. The other premises will get some argument. We're also going to, I'm going to say a little bit about how this happens, although for the sake of time, I might, we'll see. It is a premise without a whole bunch of support, but a little bit, that everything can be formalized in ZFC. All of math, I should say. All these truths of math can be formalized in ZFC. And then we're going
Yes, but before to the question about mathematics, you said that in this approach, mathematics is what is formalized in the ZFC. Then in this case, A2 is simply tautology. But for Leitgeb, it is not a tautology. So it's an assumption. So in fact, what it takes to be mathematics is what is historically taken to be mathematics.
That's, I would say yes, at least in this article, yeah. He says almost all mathematicians are going to agree you can translate a whole bunch, if not all of math, into standard set theory. And he thinks that's all he needs.
Yes, but
We'll see if
the
that's true.
point is that you can characterize mathematics in this sense independent of ZFC. Where is mathematics? Mathematics is what historically is called mathematics.
Yes.
So for example, we know that Euclid geometry is mathematics even without knowing at ZFC. And then once we have this characterization of mathematics as a sort of historical characterization of mathematics, oh, look, this is also translated in ZFC. Okay, so we know what mathematics is independent of ZFC. And we discover that ZFC is so powerful that anything that mathematics is, that you are identified independent of ZFC, is translated,
But
can
I'm
be
confused.
translated.
How do you know what's mathematics independent of ZFC? So let's say
History.
the well ordering. The well ordering, is that true mathematics? I mean, it's true in ZFC, so I need to know ZFC. Otherwise, I couldn't even answer the question.
No, okay. Of course, there is a piece of mathematics that is the piece of mathematics that ZFC make clear, of course. But
Yeah, but that's a typical example. There could be another theorem that implicitly use choice. But I don't understand how you define the theorems of pure mathematics without having an axiomatic system in which.
But so my question is the following: do you need to know ZFC to say that projective geometry is mathematics, or that I don't know, measure theory is mathematics, or that Euclidean geometry is mathematics?
Yeah, measure theory is a very good example. That if I don't have ZFC, you know, there are theorems. So is it true that
measure
you
theory
can
was
take-
developed by Leitgeb without.
Yeah, but can you take a, so the theorem says you take a ball, you separate in 7 pieces, and now you have 2 equal balls. That's a good theorem of mathematics. It's only good theorem of mathematics because I have choice. If I didn't have choice, that theorem would not be true. So I don't understand how you can separate, like, it is fundamentally crucial that I have choice when I say that this is a theorem. What is a theorem? A theorem is you prove something from some assumption using the axiom. So when I take a ball, I split it in 7 parts, I rearrange, and now I have 2 balls, I use C. So is that a theorem or not? So to me, the choice of the how do you call it, the previous slide, the previous again, I guess, the source, it's crucial to even defining A1.
So you mean that before 1908, we did not know what was mathematics?
Yeah, we thought it was mathematics, but that what satisfied my A1 was. So here you say, oh, theory of pure mathematics. So before 1908, we thought that something was pure mathematics. Was it? What does it mean to be pure mathematics? What is a theorem of pure mathematics unless I know which
What the
axiom I'm using?
community of mathematicians accept to be a theorem of pure mathematics?
That's completely unconvincing to me.
But can we not just take the source as a parameter of the argument? So whatever the source is, we can look at how much of the argument goes through, and then whether we have choice as part of the source or not, we can postpone for later.
Also, I'm sorry, No, I'm sorry, no, continue.
No, I'm finished.
Oh, just, Gauss did his work way before ZFC was ever around.
Right.
So is he a mathematician? Did he know he was a mathematician?
I'm not disputing that. I'm just disputing this as a valid argumentation. So all theories of pure mathematics are true. So is the well ordering one of the theories that you put in that list or not? And your answer would be yes, because it can be translated in ZFC.
Okay.
That's the reason
Okay,
why,
no,
so-
because it comes with, it is just using regular mathematical vocabulary, right? I do think that because it's very clear that it's pure mathematics, right? It's maybe a question of whether it's a theorem or not. And then I do think we get into the trouble of, how you define theoremhood is theory relative. And that's why I ultimately don't believe in the necessity of mathematics. But I think it's still, bad to accept it for now.
Well, I still, I don't want to hold you up.
Okay, so
I still don't understand what means all theory in pure mathematics, unless I know that I'm using one axiom or another.
I see now your point. I did not understand that your point
Okay.
was clear. So I had, when Ben presented the point, I had the same reaction, but with another example. My reaction was concerning the famous theorem that the external angle of a triangle
Right, okay, yeah.
180. So it's true in a Euclid space, and it's not true in a no-Euclid space. So how can we say that is true? And I think that the answer that we identified in the end is that the theorem that is true is not that the angles in a triangle are true, but in Euclidean space. And so,
But here it's a little.
so it's a sort of iftenism.
Right, but
It's a
it's a
sort
little
of
iffier
iftenism.
because that would have been my answer to your thing. The theorem is not the angle does this, but in this system here. But here, the system that I use to validate the theorem is the same that I'm using in A2. That's what is the problem. See, I understand how you can do this in
Yes,
your example.
in some examples it's the same, in other no.
Right.
Yes, in the case of the
As I said,
triangle.
you can also take the foundations as a parameter of the constructor, and then you do the same thing for the foundations, what Marcus said you can do with the Euclidean geometry.
So, of course, ZFC is a very particular case because in the same time a mathematical theory and the framework
Right.
for mathematics.
That to me is the major.
But so there are some part of mathematics that can only be formalized in ZFC. For example, measure theory now, Leitgeb is another story.
Oh, of course.
We have it
But now,
That's
sorry,
another
sorry, go.
Is mathematics as a concept even well defined? I don't think it is.
No, I agree.
So isn't this argument immediately circular? Because we have to define something to prove it.
Yeah.
It seems to be defining mathematics as ZFC. So A1 and A2 are essentially the same axiom. And then the argument becomes
I
circular.
think that that's the original way of stating the first person's problem as well. Also, that it's,
Oh, okay. I have not much philosophical thinking.
Well, there's a stock move that philosophers make, which is to say, there are always going to be clear cases and borderline cases. And so let's focus on the clear cases, and then we can, over drinks, we'll get to the borderline.
Okay.
And just a few comments. One way, I'm not going to actually set it out this way, but you could take A1 as sort of just pure assumption for conditional proof. We're almost not even paying attention to what it is. It's just kind of, it's going to be in the background. A2 is going to hopefully form a link between set theory and the rest of mathematics. And A3 is going to be the source of the necessity.
Let me ask another one, and then I'll stop.
That's fine.
Can we put A1 and A2 together and say that the assumption is that all theorems that can be formalized that can be translated into ZFC are true?
Sure.
That I would feel more comfortable rather than A1 and A2. I would be happier if you had an A0 that says, I'm not picking on you, I'm picking really on on Dr. Leitgeb. So I would be happy with A0 that has all the theorem that can be translated into ZFC are true.
Yeah.
Then I'm happy.
Good, we can restrict the argument because nothing essential, at least philosophically, I think will turn on that.
No, see,
Uh,
but it does.
Okay, all right,
because,
so, okay.
Like, so
Fair
why,
enough.
so then, like, so large cardinals, what happens with them, right? Because also, like, they surely are pure mathematics,
Mhm.
right? But then, well,
They're not adequately
I guess
representable.
they can be
as- yeah.
translated into ZFC, but they're not theorems of ZFC.
Yeah, I mean, I think you could say, I kind of accept one more than I do two. So I can write down the axioms, the first order axioms of group theory,
Mhm.
and say that all the theorems of that theory are true. And that's reasonable, but I don't have to know what and then we turn around and say a model of group theory is a set with certain operations. But we just imported sets into that picture, but we didn't need to. Because the theorems of group theory don't depend on the model being a set, it just depends on it being a model. But in fact, it has to be that way because otherwise there can't be a model of set theory. That actually wouldn't make sense to say you have a model of set theory because what are you saying? There's a
I
set.
like what you're saying, but then it's, so you're restricting all the theorems in a way that you're looking at.
Yeah, so you give me enough axioms, that's A1,
Right?
to describe my field of mathematics. And
Okay.
then all the theorems in that will be true in any model
All right,
in any model of those axioms. So that would be A1. And then you make another claim, which is that in practice, we know that all those things can be translated to set theory, to ZFC. So I think they are separate claims because of that. And even a little bit controversial because we can't do that for ZFC itself.
Right.
I'm quite close to Drew. So I think to me the notion of mathematics is not a very clear notion, it's a fuzzy notion. And the only way that I can describe what mathematics is what historically has been taken to be mathematics.
But do you think that what you're saying now, Marco, is kind of a counter argument against what Leitgeb is doing, or it's just not relevant to what Leitgeb is doing? So I think it's not relevant to what Leitgeb is doing.
No,
I agree with you, but I think
yeah,
it's not relevant to what he's doing.
The way in which I understand the Leitgeb argument is not that the argument conclude that mathematics is necessary. According to me, the argument of Leitgeb is not, the conclusion is not that mathematics is necessary. The conclusion is, here is a possible argument for the necessity of mathematics, and here is what I have to buy in order to conclude in this way. I show you a possible price for concluding that argument. So, in fact, the question is not whether you agree or do not agree with the premises. The question is, if you buy this premise, then you have this conclusion. This conclusion can be bought with other premises, possibly. But these are apparently some premises that are enough to conclude for the necessity of mathematics.
Well, and it'll be even a little more conditional than that, which has already been hinted at. So here, the details really are important, which is just to say we can translate statements from other areas of math into the language of set theory. That's all I'm saying. There's an injection, there's a translation function, which takes woofs from group theory, say, into set theory. So, sets of statements, I forget the operators. The consequence relation, I'm going to turn into the arrow for ease, at least ease of exposition. And we're going to do the derivation in K. And so I'm glad that so much anticipation has built because there it is. You've never been so grateful to see a derivation in your life.
Of course, the FCM can be a statement, a theorem of ZFC, nothing forbids that. In this case, the function is the function identity. To translate it in itself, what is not the problem, is a fixed point of the function. Then there are other cases in which if M is not written in the language of ZFC, and so the function
It's non-trivial. Yeah.
is not trivial.
Sorry, what
I
is
don't
phi
see what is the problem.
M and phi z? What are they again?
So, okay, so M is like you're in the original area of math. Sub Z is going to be you're in ZFC. Translate into ZFC, but corresponding. So there's one Greek letter to say the content we hope is constant, but translate into ZFC. Yes.
Can you go through the derivation and explain what the
Please,
rules are and the rules?
My pleasure. Yes.
One moment, it's completely independent. Do you see the people in the Zoom if someone?
I am not connected to, there are about 800 people.
Because we do not see the people. There are 9 people in the screen, the Zoom, and so perhaps they wanted to.
He's using my computer, so
So I connect myself. Okay.
Thank you.
So I also have a question.
Yeah.
Do you want to first go through the proof and then we ask questions about the, or, like, it seems to be
the spirit
that maybe
moves you.
you're, I'm just smuggling in a box here on line number 1. Is that really is that really granted by your premise? The
Right.
box, I mean, I see that A2 grants you the by conditioner, but I don't see why it grants you the box.
Yeah. So if we look, sorry, let's go back to A2. Yeah. So there's a translation
Yeah.
into ZFC. And what perhaps I may have missed something, but I'm more or less appealing to authority, that this translation can always be carried out, basically, in such a way that of necessity, the original, both the well-formed formula, the original theorem in particular, and the translated theorem are going to be materially equivalent. If you're asking about the box, but basically he says, well, the translation will necessarily work.
But this is already a statement about all possible worlds, right? So maybe that's what Alex. That's
That's the worry about
Yeah,
granting.
like the worry is like if you start with 1, it's not a surprise that you end up at 9, right? So that's the problem.
Yeah, but that's his point is that now we're looking at the premises. It's not a matter of the validity of this argument. It's whether what's the cost of accepting the argument.
Exactly. So for example, number 1 follows from the biconditional. The biconditional is a tautology. But that's doubtful that you can argue that it's a tautology, right? Because M and Z are in different languages. It's not even clear that, right?
Well,
So
that's-
the fact that a translation exists, I don't see how you get from there to phi M biconditional phi Z being a tautology.
Right. Yeah. So well, it's going to take a little more than Leitgeb gives in his paper to actually get the conclusion. The conclusion will be closer to what's Drew and if I remember correctly, we're talking about, which is we actually need to get the axioms in there from, say, group theory. It's not enough to take a theorem from an arbitrary area of math. We have to import more, translate more with that theorem, rather. So I think it might look, the conclusion is going to be weaker, but it might make the first premise more plausible or palatable. First, I'm presenting it, and it may need some more reconstruction, but I'm presenting it a little closer to the way he does in the paper. And so you give me 5 more slides and then see what you think about the first slide. And you might be right, I'm not denying.
Sorry, for the people on Zoom, now I see you, so you want to tell something is enough that you put the icon of the question and I see you, okay? Go.
What does it mean phi M and phi Z? What's the meaning of these?
Yes, phi m is supposed to, now we're sort of in this common system K of modal logic.
What is the sentence? Phi M is the sentence.
It's a theorem of an arbitrary area of mathematics.
So X is a theorem of the area of mathematics M. Is that it?
Yeah.
It's something like Cayley's theorem.
Okay, and FZ means?
So phi sub z is the translation, the result of the translation.
Two-set theory.
So I can read that as it is necessary that if a mathematical statement is true, if and only if it can be translated into.
Yeah.
Okay.
Yes, very well. Another premise, which this is where the main action is going to be, is where, so it's true the box is in the first line, but where we go from the antecedent not being necessary to the consequent being necessary is in line 2. And so the work that I'm going to try to do to show like where do you actually get, where does it come from? What hack do you pull it out of? It has to do in ZFC, how does set theory allow us to get necessity from something? The third line is the premise that I said, we're just you start out with some truth. Let's say there's one truth of mathematics, the Cayley's theorem. That's the one. It turns out to be true. We're just going to grant that it's true. We do need that to get off the ground. So it may be too high a price. There's some costs. The next moves are fairly straightforward, either from K, the distribution of the box, or propositional modus ponens by conditional elimination. But if you have any other questions about this, that's okay, because this is what we've been working up to this point. I think the idea is that from line 2, it's true that line 1 facilitates the flow of necessity, but like where it comes out of the ground is in line 2. We get it from set theory. Patrick.
Yeah, so in premise 2, is the box coming from the fact that we're supposed to be taking set membership and equality to be rigid?
Yeah.
Okay, yeah, maybe talk about that a bit.
Yeah,
That's really important. Yeah.
I have many slides.
All right. I don't want to derail you
slides
anymore. Yeah.
We'll see if we even get to it.
Okay.
Yeah. Because, and why is it really important? Why would you say?
Well, I mean, first you might just want to try to justify that. Like, why do you think that's true?
Yeah.
I mean, why would set membership be rigid?
Yeah.
Or just describe what rigidity is.
Yeah. So, we'll get there. And the conclusion is supposed to be, so thank you for bringing up that point, the conclusion is supposed to be that this arbitrary theorem of mathematics, and therefore we can sort of, in the meta theory, universally generalize over all theorems of mathematics. The arbitrary theorem has gotten necessity. That's the last line of the derivation. So it is, I mean, in K it's valid, but as we've pointed out, there's some questions about the premises. So let's see. Indeed, they end up being a question about the conclusion. So what's actually happened? This is my take on what's actually happened in this derivation. So we take that theorem, we translate it into ZFC. But you're right, it's the theorem on its own. Just you could take any statement and re-describe it using set theory. That doesn't mean it's true in set theory. So what we need to do in order to get something that's true is to take, for example, the axioms of group theory, bring them in with, translate that set of statements in with, for example, Cayley's theorem. What we get then is really the structure of the derivation of the theorem from the premises to the theorem. It's not enough to translate the theorem. We have to bring with it a sufficient set of grounds, of proof. Basically, we have to translate into ZFC. By the nature of the translation and what happens with box and the derivation, what we get back is that we've necessitated the axioms, and we're assuming, mathematicians know how to do deduction. There's a consequence relation that holds, and then we get the necessity of the theorem on the other side. So what we have not done is we have not derived something which is equivalent to the theorem. John.
Sorry, I still don't see where does the necessity now come from? Because I'm wondering.
Yeah, in fact, maybe I should have rewritten this, the derivation with the conditionalized. I forgot to do that.
No, that's. Can you go one slide before, one after? So the third to the last bullet point, you said ZFC plus philosophy yield.
Yeah.
So why?
Yeah.
That's my question.
Yes. So this is what we'll get to.
Okay.
Basically, philosophers think identity and we also need set membership have certain properties. Identity, philosophers think is necessary. We're going to do something similar with set membership, and then that's where the necessity is going to come from. Ultimately, those are the grounds on which this derivation rests. It's a necessity of, we're assuming set membership and identity.
So identity being necessary, that's kind of Kripke's not his whole thing, but a big chunk of what he thought about rigid designation and all that. Right? Okay. So now I'm kind of situated properly, but now I don't see how membership is of the same kind.
Yeah.
As identity.
So this is what I was complaining earlier. I wanted to derive necessity for set membership from axiom of extensionality, necessity of identity, maybe Leibniz's law, throw in, a few other things that philosophers are okay with.
Mhm.
I wasn't able to do it, but I think what I'll be able to show in what follows is that we can assume the necessity of set membership without blowing the system up. But how far I get and how plausibly you find it, I'm interested to hear from the mathematicians. Because I moved a few symbols around, but I probably messed it up. Jonathan.
So I could ask if 0 is an element of 1, and the answer is it depends on the encoding.
Yes, right. Yeah.
CFC.
Yeah. We're also gonna eventually get to the cumulative hierarchy, also known as von Neumann's, even though it was Zermelo, which beginning with the empty set and using union to build up.
And so, because that's
Transitive.
fixing that's like, you said you did a translation, so that's going to be fixed by the translation. So there is going to be some fact of the matter
For that translation.
for that translation, and
Yes.
you have to pick. So that answer, like that question will still be answered. You might not like that you get
An answer.
an answer, but
Might not like the answer.
I was like, but also,
Yeah.
it's not that big of a deal.
So in fairness, I don't think this really hinges on ZFC per se as this pure theory of the epsilon relation. There are alternatives like structural set theory that takes sets and elements to be just of two separate sorts. So there's not even a question of whether 0 is a member of 1. That's a nonsense question.
Yeah, type theory, it doesn't make sense there.
Right, right. So I think there are provably as strong theories as ZFC that would do the same job.
Although we haven't.
If those kinds of questions bother.
We haven't seen it yet, but it's actually the necessity of the axiom of extensionality that does the work. So you
Yeah,
do
that-
set extensionality, which I don't know
That I
what
can
you get
believe.
the equivalent of in non-set theoretic foundations. I'm sure there's something, but
But again, it's just
Yeah.
that ZFC is a parameter of the argument, and like you can take any other foundational theory you like and run something
no, you
similar.
can't. I just told you that it relies on the axiom of
Why can-
extensionality. That's
Okay,
not an
why
axiom in
can
other
you not,
foundations.
why can you not make similar arguments for other foundational systems?
Because
Choose a
they-
foundational system.
Because their axioms aren't necessarily self-evident and require
Oh, okay.
only.
So you think the axioms of Strelo-Frankel set theory with choice are self-evident?
No, I think the axiom of extensionality is, that's only one of them, and two, I don't think that, Hannes Leitgeb thinks that.
Interpreted through Ben, so,
No,
Any
but I know
faults
this
can be
paper very well,
attributed to-
that is Hannes's position.
okay.
Just something to say with like the arguments about like, oh, it's like, if you buy these things, I think Hannes does buy all of the assumptions. He does present it in this, maybe you don't like them, but
Well,
Well,
you're right
honestly, I
about
think-
extensionality being really
yeah,
pretty
that's true.
pivotal to this picture.
Yeah.
Have I misrepresented him so
No,
far as far
no,
as,
no,
no,
no.
am I doing like, okay, I don't want to do that if I do nothing else, Jose.
I know this is not a statement of mathematics, but membership being necessary, would that imply that if I am a member of a gym, I am member of the gym in all possible worlds?
Right, there's something very strange about talking about set membership. Is it an essential feature of anything that it belongs to maybe that it belongs to some set, but any particular set? That sounds wildly implausible.
Has to be for pure sets, right?
That,
Has to be for pure sets.
and that's where we're going. And that's why, yeah. Yeah, yeah, you see the road ahead now.
I was like, you can't wait to see if Mug is going to make it comment.
That was my-
I was like,
Then I started waiting and I'm like, do I keep waiting?
you got
No,
it.
keep going, keep going.
All
This is your
right.
chance, this is your chance.
Don't take the chance.
All is thinking,
So there's one potential shortcoming of this derivation is that it might not get you as much. It looks like we got the necessity of this arbitrary theorem. But maybe we don't get, the conclusion isn't quite that strong because it's got to be conditional on the axioms from which it came. It's got to be the interior angles of the triangle being 180, we need Euclidean space in there. We translate that to, it's all got to come together as a package in the ZFC. And so maybe we're not getting as much necessity or any categorical necessity as we want. Maybe it's all still up in the air. Or,
But, sorry, not clear. What are, according to you, the necessary assumption about the ZFC that make the argument work? Come back. It's not clear to me completely.
here?
See, the only premise are 1, 2, 3, according to you.
Mm-hmm.
And so what we require to ZFC that satisfy premise 2.
Mhm.
This is the,
One.
This is what we need from it.
No, 2. That's it.
and also 1.
We also, I mean, there may be another way to conduct the
Because
deduction.
the premise 3 is not relevant, because what we are proving here, that it's true, is necessarily true. If you deny that it's true, of course, it's not necessary. So premise 3, in fact, is for 3.
Not really a live issue.
Not necessary, because of course, what we are arguing is not that mathematical theorem as true, as necessary. What we are arguing that if true,
If true,
they are
then
necessary.
necessary. That conditionality is built in.
Okay, so 3 is
Might as well
for free.
or do
for
a
free.
subproof.
So the real problem is 1 and 2. Okay, good.
Yeah.
Okay.
Yep. So is this a problem? Maybe not. So the problem again is that what we got was not the theorem on its own, but this conditional form, either with the arrow, the turnstile, or maybe a double turnstile. There's some necessity. If the axioms are necessary, then the theorem is necessary. We didn't get the theorem is necessary. All right. Well, maybe that's okay. Maybe that's what math is. Maybe we got it right in the end. We noticed something, and this is actually what's really going on. Is what mathematicians do is they snoop around looking for desirable in one way or another axioms. They choose their axioms with certain goals in mind, and that takes some work. And the rest of the work of what they do is they suss out the consequences of those axioms and see what they get. And that's math. That's what mathematicians do. And if that's right, then it's maybe not such a big deal that it's a conditional on the not only the truth of the theorem, but on the axioms from which the theorem is derived. It seems to me that yeah.
Question, under this if-thenism
Yeah.
view,
Yeah.
is then everything is then necessary. So every kind of formal, so whatever formal system I have, right? So I continue kind of deriving new strings in my formal system. So all of that is necessary. But that's also all there is to necessity. So, I mean, maybe I could accept that, but that would be kind of, indeed, a little bit of boring conclusion. So it's like the example we discussed with chess, right? Chess is the same in all possible worlds, because if you change the rule of chess, it's not chess anymore, but another game.
Yeah.
So chess is necessary. Okay, but that's not really an interesting statement.
Well, I'm going to try to make this work in every possible world, at least in principle. The chess can be played in every world. We're going to try to show that. We'll see if you're convinced.
Okay.
All right. So I think another response. I mean, you could now they have to be accepted axioms, and there has to be a theorem on the other side, and that's what gets translated in, and that's what gets the necessity on the other end. It's popped out. But I think Leitgeb is, I'm not sure that that's what he was aiming for. I'm pretty sure that wasn't what he was aiming for. For one thing, he's pretty, the way he talks about it, at least as my understanding, I couldn't misunderstand, but he's talking about the theorems of mathematics, and he just leaves it at that. That's what he wants to be necessary. For another thing, theorems can, often, if not always, be derived from more than one set of axioms. So it's unclear, is there a strong enough connection between the axioms and the theorem to justify importing all of them together into set theory? And we gotta take it as a package. Well, you got many to choose from. The whole point of if-thenism was part of what mathematicians do is choose among different collections of axioms. So maybe we should try to avoid this conditional result, but we'll see how close we can get to that. I thought I could do it, but all right. However, I mean, another approach is, well, the axioms of math are more mathematical statements. They're meant to be assumed to be true, or maybe there are different kinds of support for them. But fine, we'll translate the whole package into set theory, and then what we're going to do is we're going to find independent necessitation for the axioms. But it seems to me that this might reproduce the whole conditional necessity problem. Because how do you justify, it's a regressive justification. How would you justify the axioms you chose to be the axioms from which the theorem is derived? Any premises you have behind those, well, now those are going to get translated in, but now we're going to have another conditional that gets translated into something. Something to think about, but this might be a persistent problem, is all I'm trying to justify. I was going to use an analogy earlier, line 2 being, picture this as an elevator, which goes from the ground floor of plain truth to the penthouse of mathematical necessity, where the box is either the penthouse or the car or the carriage that you take up the elevator. All right, so we're going to ride the elevator up. How do we do that? In other words, where is the necessity? I've been teasing you this whole time about necessity. We get necessity out of set theory. Well, let me try to convince you that there's something to that. As already hinted at, what we're going to use are the identity of the necessity of identity, which philosophers take. This is unproblematic for philosophers. We're also going to try to do something as similar as possible for set membership, and we're going to see if it works out, basically. All right. So my strategy for doing this is take identity and set membership, and we're going to put the necessity operator onto the axiom of extensionality. So why is this central? A lot of people take the axiom of extensionality, which we're going to see on the next slide. Well, a couple slides, because first I'm going to go over designation. The axiom of extensionality is often taken to be what defines sethood. Like, you can't have sets without this axiom. Now, I don't know if that's universally agreed upon, but I hear that it's often taken to be essential to set theory. I'm going to then show how to construct basically construct in any world, or why it's necessarily constructible or necessarily existent, the empty set. And then I'm going to show that the cumulative hierarchy necessarily follows from the empty set. It sounds fancy, but I don't think that any of this is original. I'm just trying to explicate what Leitgeb did. So Saul Kripke has been mentioned, and he is a very large figure and did cause a revolution in philosophy. And at the heart of the reason why, from what I understand, is a book called Naming and Necessity. It has to do with the philosophy of language, but there was this kind of nerdy result that was originally derived, I think, by Ruth Barkin, or she began the proof, and then it was later carried out by other people, of how you derive this necessity of identity, and then it's pretty much been taken as a principle by most philosophers. So what it says is the identity relation is special. So if you have two variables and they flank, for example, x, y, flanking the equal sign, which we read as identity, and it's true, then they're not two different things, actually. X and y, you've slotted one object into both openings in that relation. Now, if that's true, through various arguments, not all of the details of which we will rehearse here, it follows, many people believe, that that statement is necessarily true. We begin with plain truth and we get necessary truth. And indeed, this is the pattern we saw in line 2 of the derivation. You begin with the plain truth of a statement, and you end up riding the elevator up to the penthouse of necessity. Okay. One key feature, however, is that whether they're taken to be objects or expressions naming an object, it has to be the same thing, basically. So whatever's on either side of the identity sign has to rigidly designate. The idea of rigid designation is that it always refers to the same thing. So for example, the inventor of the bifocals is a description, and in this world, it refers to Benjamin Franklin. I think, right? That's the example.
There's a world in which
He did in
that's
some
fine,
ways.
or not.
Depends if you are in America or in Europe.
Yeah. The Americans say it's Frank, yeah. Although he did spend quite a bit of time in Paris. But this description does not rigidly designate, because in this world it refers, let us agree, for the sake of argument, to Franklin. But in some other world where Benjamin Franklin never lived, it refers to someone else who happened to invent the bifocals. This description picks out different objects depending on the circumstances. All right. And that spoils the necessity of identity. But as long as you have rigid designation involved in the true identity statement, then it works throughout every. You can change the circumstances, the identity statement is going to stay true.
Which kind of would be designation?
Yeah. So a name is often taken to, or at least Kripke argued, the reason this book is called Naming and Necessity, he argued that names are rigid designators. Mm-hmm. And they're intimately connected to this whole identity.
So Ben Franklin is Ben Franklin in every world,
Yeah.
but the inventor of bifocals
Can change from world to world.
may be different.
Yeah. And to give another example, which is often used instead of an individual person, natural kinds. And I struggled a bit to explain why this is so important to philosophers and what it really means. But the example given is to Kripke and I think Putnam might have done the water thing in particular. But anyway, in any case, it's an essential feature of water is identical with H2O. That's its defining feature. It took us some time to figure that out, but we did, and we found it. We know it now. We did experiment, it's posterior, a posterior, that's okay, we know it. It's a true identity statement. It could not be otherwise, because you go to any world and find some clear, tasteless, liquidy liquid that's thirst quenching, and it's not H2O, it's some substitute compound. It's not going to be water. The water, if we use that as kind of like a name, is not going to actually refer to this other substance. Because water is H2O, not XYZ. It's a tough, I'll take suggestions for how to explain necessity of identity and rigid designation.
It's the same as the chess argument, essentially.
Yes. So Benjamin Franklin, let's go back to Benjamin Franklin. That's a good name. That name will refer to him and only him in any world where he exists. And where he doesn't exist, it doesn't refer to anything, but it's always going to be faithful to him, so to speak. So, yes, that is the point you just made. Okay. Similarly for water, water is going to refer to only the water. It's not going to refer to XYZ if water isn't there. This really isn't that important, but if anyone has questions about it, here is one derivation of the necessity of identity with the necessity of self-identity, which is taken as a premise. That there's no way that X is identical with itself could be false. You use part of Leibniz's law and you get X equals Y. You substitute. So what are we going to do with all these ingredients? I've thrown a whole bunch of stuff at you, hoping that this will help explain what's going to come next. So I've said that axiom of extensionality is supposed to be really essential to what sets are. So one thing we need to do is to see, can we necessitate this, the axiom of extensionality? So here's an attempt. Here's the first line. I'm going to use the biconditional version, but I don't see, usually it's the left to right. I shouldn't say usually. Sometimes authors only use the left to right direction from the universal quantifier to the two sets are identical.
I do not understand why Dutch extensionality means, what does it define what it means to be a set. It only defines what to be the same set of. What it means to be a set is defined by all the action of ZFC, not only by extensionality.
Okay.
Extensionality
That's
since
fair.
we give an identity condition for set.
That's fair enough. Yeah. But I think as a condition of identity, it will play an important role.
And
It's
but
the identity.
But I think that the reason why you might say that it's defining what it is to be a set is because this axiom is telling you that the only thing that distinguishes sets from each other is, and so like, you know, is their members. So all that it is to be a set is to be composed of some particular elements.
Selection of them. Yeah.
I think it's also a different kind of axiom in the sense that the others are existential axioms. All other axioms say that in the following situation, there is a set with a certain property. So they're inductive, so to speak. But the axiom of extensionality is the only one of the set theory axioms that doesn't have that flavor.
No, also the axiom of infinity.
Sure, there exists a set such that blah, blah, blah. So that's an existential statement.
Yeah.
And all other axioms of set theory are existential statements.
Then?
Except this one. So there is a difference in form in the axiom of extensionality from all other axioms of set.
Okay, but this means that the axiom of extensionality is enough to explain what does it mean to be a set?
Well, I mean, it's the only one that's telling you how a set relates to its elements. How all sets relate to it.
Well, no, it tells you the identity of the set. What it,
It gives the condition of identity of set.
I'm happy with
Yeah. I'm just pointing out that it does have this
No, to
different.
give a condition of
There's different
identity of
formal-
something
there's a different
is a
formal
large part
equivalent.
of saying what these things is, but it's not the only thing.
Yeah.
So
Fair enough.
No,
to
fair
give what
enough. I
is a
mean,
set.
sets could be heads of cabbage as long as they have this epsilon relation.
Yeah, because like I think that it is a philosophical point, but I think it's a philosophical point that people accept that the axiom of extensionality suffices to define sethood, not just identity of
Fair enough.
set.
Fair enough.
One
You know,
of the
so-
this axiom is a set is completely
So
determined by
with the
itself.
axiom of,
That's right.
Yeah.
with the axiom
That's
of
the usual.
essentiality alone, I can derive a Russell paradox. So how can I block a Russell paradox? When we say why we say we need axiomatic set theory in order to explain what is a set? Because with a naive notion of set, we have a lot of paradox.
No, you can't define. You Russell's paradox needs one. It needs an existential, right?
Sorry?
It needs some. Oh my god.
It needs a separation axiom.
Yeah.
Of course, this is my point.
Right.
Okay, but so with just axiom of extensionality, you don't have any sets.
We haven't
You
gotten
can't
this
get a paradox from it.
I am not saying that axiom of extensionality is not relevant. Of course, it's fundamental. But I say that it's not enough to explain what is a set. Because if I only take the axiom of extensionality, I can still derive a lot of contradictions. And so when I derive a lot of contradictions, it means that my idea of what is a set is not well precise.
From
I
the,
don't
from
think
the
I-
axiom of extensionality, you cannot derive pretty much anything.
Sorry?
From the axiom of extensionality, you pretty much cannot derive anything.
Can't derive an
You cannot derive
contradiction.
anything. You don't even have an axiom that tells you that there is a set. You cannot derive anything from the axiom of extensionality alone.
Okay, so I am exactly. So perhaps it's not clear what I mean.
Okay.
So the story that we usually tell, perhaps the story that we usually tell is wrong. But the story that we usually tell is we have a naive notion of set. And with this naive notion of set, we derive a lot of contradiction. And so this naive notion of set cannot tell us what is a set. So in order to explain what is a set, we need a axiomatization. Okay, now I begin my axiomatization. I begin my axiomatization and I say, okay, the first axiom is the axiom of extensionality. Is this enough to block the contradiction? No.
Yes,
And so-
it is. It is enough to block
Why?
Because no sets exist. If all you have is the axiom of extensionality,
Okay, maybe
no sets exist.
maybe I can
right?
rephrase this and then please let's.
I do not understand.
Continue.
Okay, go.
We could just say it in this way. Extensionality could be read in this way. Set is completely determined by its elements.
Sure.
Therefore, if you tell me what the elements are, then this is going to be a set. So these are two different things, right? Extensionality is a set is completely determined by its elements. The other thing is, if you tell me what the elements are, I can construct a set. And these two things together, this is a contradiction. Because I could tell you the set of all sets. Therefore, it exists. But extensionality alone is not enough. You need this other thing, that there are different ways of.
My problem is not this. My problem is that with the axiom of extensionality alone, I have not made enough clarification of the notion of set to avoid to derive contradiction. And what he's saying, it seems to me, is not true. The axiom of extensionality is enough to block any.
I think we're at an impasse. We agree to disagree and let them continue.
Okay, let's go.
It's a very interesting discussion. However, the axiom of extensionality will not be alone for long. I have brought friends to play. So I may have overstated the case a bit to say AOE helps to define what it means to be a set by offering a criterion of identity and indeed distinctive. So let's slap a necessity operator on and see what happens. So what I claim happens is we're working within K, the box distributes. We're going to call upon now the necessity of identity. And at the bottom line here, we get this. Now, of course, this is conditional on having at least one set, which we don't have yet, but suppose for subproof that we have.
No, you don't need it.
Yeah.
Universal quantifications are true even if there's no sets.
It could be true, yeah. So we're going to end up being vacuously true, but
My favorite case.
then you'll be well pleased. Because we're going to do even more with the universal quantifier in the box are gonna have a good time. What I'm going to say is, what can we do now? What can we, logically speaking?
What was NOI, sorry?
Hmm?
What was NOI? N-O.
Oh, necessity of identity, sorry.
Necessity.
Yeah. So we've gotten to this point, so necessarily for any X, it belongs to S if and only if it belongs to S prime. Think of these as two names, if they are identical sets, for the same set. We may not know to begin with, but if they are, then we're going to see that they have exactly the same numbers.
They've got to be rigid designators, right?
Pardon?
The set names need to be rigid designators, is that right?
Yes. Yeah, that's right. So if there is something to name, and if we have named it, and the names co-refer, we have a true identity state.
Isn't it just that they're objects?
Well, so yeah, we're also treating sets as objects. That's right. Yeah, Peter.
How does that last statement follow from the previous implication? And you need to assume that S equals S prime to get the bottom line?
Yeah. Yes, so I believe I said on the supposition that S equals S prime is a true statement. And since I haven't constructed any sets yet, you're right to be a little suspicious of that, but I'm just building the dramatic tension for what's to come next. One can try. So can we get any further? How do we're seeing basically how does the box interact with the axiom of extensionality at this point, and the necessity of identity. Okay. Well, Ruth Bark and Marcus, I think this is a wonderful picture of her, and I would try to include it in everything that I do, if appropriate. They have made some cartoons where she's speaking in her own. So I mean, there's some suspicion that one could do quantified modal logic, but no one had actually done it before Ruth Bark. And she's kicked at the door down and said, I'm going to do it. She's one of my heroes. So. And I think that is a lovely picture of her. So it's not totally gratuitous, however, because what I'm going to do to try to get to work with necessity and the axiom here is the CBF, the converse Barkin formula. you'll notice that the antecedent there has a box for all, and this is the last line. We have a box for all. Okay, let's do a couple more moves and just see what happens. All right, well, we can drive the box in a little bit. So now we have it in the components of the biconditional. One could wonder how much we've actually accomplished here. And indeed, I thought I could accomplish more. As I think I mentioned, I was trying to derive the necessity of set membership, but I could not do it. I think for Leitgeb's purposes, it might not actually be that important. But basically what we have here is, just as with the piety example, one of the problems we're going to have is that this could be vacuously true. Biconditional is a symmetrical operator. I mean, both of the components could be false, and the whole thing is true. There could be no sets, and the whole thing is vacuously true. So to make any progress at this point, it seems to me, we've made a little progress with the converse Barton formula in terms of, so far these things are interacting. As far as I can tell, they haven't exploded yet. We haven't derived a contradiction. I hope I didn't do that in the process. But what we need to do is to verify that there is a set. And indeed, we want to have certain properties, among the most important of which is going to be that it exists necessarily. How am I going to get a necessarily existing object? It's an old trick. It's not my invention, but we're going to construct a necessarily existing set. And the other problem is that we have this sort of vacuity. We don't really know whether or not X does belong to S and S prime. This biconditional is true at each world, just as long as you're consistent. There's a problem of, I'm not putting this very well, there's a problem of co-extensionality, co-varying co-extensionality. So you could have a set, two names for that set, and you start off in this world with Ben and Jose. S and S prime both name this set, the Ben and Jose. We go to another world, and one of us disappears, sad to say. Only one of us is there, but that object still belongs to both S and S prime. The biconditional is true, but they're not the same set. The set has varied, but it's varied in a way so that it doesn't make a difference to this statement. There's a problem of covariation over worlds. All right. So the way I take care of the covariation over worlds, which I haven't been able to explain very well, and which may not be important, so I won't dwell on it. But this is where the one point I will make here is that this is where the assumption of the necessity of membership comes in. So if you'll recall, I was trying to derive this somehow by playing with symbols, and I couldn't do it. So what I'm going to do is I'm going to assert, as Leitgeb does, an assumption. I'm take as granted that set membership is rigid or holds of necessity, and distinctness or non-membership also holds of necessity. And I'm going to call it necessity of membership. And there it is. If Jose and I both belong to a set, S, and another set prime that happens to be the same set, then necessarily we do these sets that you can't change over worlds. Now we're modally fixed. And then you just add that you modify AOE by adding that in. It's long and gnarly, but it's straightforward.
I suppose that you are using here belong to only with respect to pure set theory.
Yes.
Because when we take a set, not pure set theory, this is very, very questionable.
Right. How could it be plausible? So I think what Marco's asking is, okay, it's an assumption, but is it at all a reasonable assumption?
Mm-hmm.
For contingent objects, no. Because they do vary across worlds. They pop in and out of existence. They're not well-behaved modally across all possible worlds.
Well,
Ben belong to the set of the people in this room. Of course, it's not necessary that Ben belong to the set of people in this room.
Right, yeah.
That's not a rigid designation.
Right. The people in this room isn't rigid.
Name, you can list the names. Put them in, yeah.
Well, in which case you will be among the list, so then it is necessary. If you are indeed, if Ben is indeed.
So the set of the names could exist in every world, but the objects named will not. So the set of the people in this room will not exist in every world.
So this is where you're talking about pure sets.
Yes, it's an assumption, maybe I didn't make it clear enough. It's a pure math, pure sets, very purist.
So no set that contains Socrates.
So right. The set containing only Socrates doesn't exist necessarily because Socrates does not exist necessarily. Even though if he exists, surely we can form a set with him. But we need something that we can always form a set on in every world. How can we be assured and know enough about this in order to make it at all plausible that we can do what we want with set theory? It's going to be pure sets. It's going to be the von Neumann hierarchy, or the misnamed von Neumann hierarchy. So the first step is you construct the empty set. That's where the hierarchy begins. Well, okay, how are we going to do that? Well, it's a trick Frege had. It's nothing. So that's what we're doing here. And in particular, what do I want my desiderata at this point in the argument? I want sets that exist at every world, necessary existence. I want them to be at least constructible in every world in the same way, so that we can kind of be in touch with them in the same way at every world. And then you can sort of identify them nicely. We'll see if we achieve all these things. So here, I'm not sure this is the best way to put it, but I put it in terms of instantiate. We talked a lot about identity. Well, let's instantiate one of these identities. I've just had these schematic letters, which are granted to rigidly designate all the time. Well, they're not naming any. Okay. So we're going to have a true identity statement, and we're going to use that, a certain object to construct that identity statement, to plug it in, and that is the empty set. How do we get the empty set, Alex?
Sorry, just a quick question. Frege did not invent the empty set, or did he? Like, what is due to Frege?
Yeah, is
That's definitional.
Yeah.
Sorry.
No, I suppose Cantor invented the empty set.
Yeah. So what is okay? This definition is remarkable enough to contribute to somebody. I don't kind of.
No, I think that formulation of the empty set to say that this is a way of. He was working in naive set theory, and that's a perfectly good formation of a set.
Mm-hmm.
And he was saying, "Look, see, there it is."
Mm-hmm. Why is it interesting to have this formula? For I mean, I can think about the empty set without that particular formula. So why is that innovation? What's the importance of that
It's
innovation?
going to show that the empty set necessarily exists.
Yeah.
Second.
It's going to be used to show that the empty set necessarily exists.
Yeah.
In all worlds.
The formula refers to the identity, in this case to the lack of identity, to the negation of the identity.
Which is
and the identity is necessary.
Yeah.
Oh, I see. Because you already know that the identity is rigid. Okay.
Yeah,
That's
yeah.
it.
So
Okay,
it's
thanks. Yeah,
bootstrapping.
that answers one.
It's a necessary false
Yeah.
on the inside. Was that everything between the brackets goes away? You only have the brackets. What does that represent? The empty set.
I have a problem here. So this identification, either you have an action that tells you that the Dexter set exists, is an action, or in order to accept that this gives you the existence of the empty set, you need to accept a form of comprehension.
Mm-hmm.
By the way, a form of comprehension that is not a form of separation. This is pure comprehension. Pure comprehension is not admissible in ZFC. So I don't know how you can construct the existence of empty set in this way without the comprehension, but we have no comprehension in ZFC. We have only separation. So what is the set in which we separate the empty set? We need to have at least one set in which you separate the empty set.
It's not separation, it's not union, it's not power sets. I'm sort of taking something for granted.
You need to start from somewhere to separate the empty set.
What about if you claim by axiom the existence of a set that doesn't contain any element?
But this is
you prove by extensionality that this set is equal to this one And therefore, from here you can derive.
Of course, you can.
the
This you can
necessity of
do.
this existence.
That is, of course, you can do. But you cannot do only that. This is my point.
This slide needs revision. That's
So you
okay.
could also assume that in every world, a set necessarily exists.
Yes.
And then the empty set will necessarily exist in every world by
it has to,
Frege's,
whatever.
by using separation on whichever set happens to exist.
Yeah.
Right.
Yes, not empty domain.
So as long as every world has a set, every world will have to have the empty set.
Yeah.
Interesting, you start by assuming that there is something to prove that the set that contains nothing exists.
Well, yeah, you know,
only have one
it's just
set.
like the numerals, like 0 got invented after the rest of them, you know?
There's only one set, it has to be this one.
If you were to grant the existence of any set, as you're saying, it would be the empty
World
set.
with nothing would still be this one.
Marco was making a fair point, but you're also kind of seeing where it's going, and you're okay with the argument. But that's a very nice point, and yes, I got sloppy here. That's true. I did.
So that's added to the cost.
No sloppier than Frege. So
Price is.
Yes,
I'll take
but the
this as a
difference
compliment.
between him and Frege, Frege did not know ZFC.
exactly.
So Frege believed still in comprehension.
Yes.
So maybe the price will go up a bit further than I thought. That's a fair point.
We need to accept that there is at least one set.
Okay.
Whatever it
Well,
would be.
I don't know. I'll think about
In
it.
each world.
In each world.
And for some people, that might be a high cost. I think. But if there was going to be even one set, it would be. Okay. And so the bottom line I want to claim is that
But
we do-
remark that there is a very simple way out of this. It is to argue, as a lot of people argue, that first order logic is enough to prove the existence of one object. And then you don't need the empty set axiom. So in many formalization of set theory, the empty set axiom is not given because we suppose that insofar for any x identical to x, so exists one object that is identical to x, or exists one object. And when you put that in the language of ZFC, so the model, I said, so it is the set. Finish. So we don't need the existence of the empty set. Then for separation, you prove the existence of empty set.
But
Under the condition, of course, that you accept that first order logic prove the existence of one object.
Yeah.
What
You
is to
accept that
me
concept.
quite absurd.
Which is
That's nuts.
weird. Yeah.
Sorry?
That's crazy.
It's crazy. But this is what a lot of people does. And in many formalizations of theory, there is no the action of the empty set. Because the action of the empty set is derived from first order logic by this argument. For any x equal to x, then exists an x that is equal to x, and then etc. etc. Yes.
But that's
I believe you, but
that's
And
an
to be clear, it comes from the model theory, right?
of first order logic. Yeah. So it proves what follows from first order logic is an existential generalization. There is an x such that x is identical. But what is the object? We don't know anything about it. I want to.
Here is one, the empty set.
But it's,
No, I do not like at all this
no,
argument.
okay, good. Then we're in agreement.
I found that this argument incredibly wrong. But still, it's an argument that is very often used to avoid the axiom of the empty set.
Yeah. Okay, so there's one option. All right. So now I thought I had legitimately achieved the instantiation of the empty set is identical with itself self-identical, but maybe we've not legitimately constructed it. But granting that we have and bypassing that, tabling that issue for the moment, let's see, what do we get? This is basically following the derivation I showed you earlier. What it's saying is if we take what we got by the converse Barkin formula, and we're just plugging in the empty set now. Well, it looks like we haven't run into disaster yet, I think. If I did discover a new paradox, I guess that would be fine, but I don't think I've hit a contradiction yet. What I meant to do was I'm adding the empty set. Has something gone wrong? I'm just checking. I don't think anything's gone wrong. But if anyone has a question, comment, sorry.
Well, I just, this is a throwaway. Just, the usual problems with using the converse Block-in formula and the Block-in formula, just that they require like a fixedness of domains. So converse just requires that it doesn't decrease, but then yeah, it feels like that. That's another place where it does seem like you are committed to the existence of at least one object.
Yeah. So in the paper, Leitgeb used the Barkin formula. In a way, I don't. Well, I thought so. That's why you got the cartoon with the converse Barkin formula next to her wonderful picture. But you'll notice in where we're heading does not have a diminishing domain. It has an increasing domain.
Yes. So that's why I was like.
So I thought, well, at least we're paying a cost. We're gonna have fun while we do it. The credit card debt is going up. We're spending a little bit. That's how we do it in MPP. All right. So the cumulative hierarchy is this basically so necessarily X belongs to the empty set. That's false. The biconditional is true, but each component is false because nothing belongs to the empty set. In any case, but yeah, moving along. Okay, this is how I think, I may need comprehension, but I think I used union correctly. One can construct the finite initial segment of the hierarchy using power set. After you get to a limit ordinal, you need to use union. So I thought, well, why don't we just start off? Anyway, what you do is the base step is the empty set, and then you begin accumulating. You take the previous stages, their union forms a new set, and you keep building a transitive hierarchy.
Technically, you actually also need replacement for this.
How so?
Well, because you've given names, you've indexed a family of sets with natural numbers or with an ordinal.
Yeah, right.
A limit ordinal. But now you don't know that they have formed a set without replacement. And so that's exactly where replacement got invented, was for this problem. Right? Of how do you make this accumulation continue at limit ordinals? You have to know that all of the V1, V0, V1, V2, V3, that they together form a set. And you only know that from replacement.
Sorry.
But I mean, your basic picture is exactly right, but.
Okay, good. I didn't mess that up.
I think there's a problem in this picture.
I was so close.
What to your point? Sorry, can you repeat me clearly?
Yeah, if you just take empty set, power set of empty set, power set of the power set of the empty set, and so on, and all the unions that you can get legitimately from that, right? You take all of those. How do you know that that family of sets is a set? Because that's the only way you can apply the union axiom at the limits. So how do you know that that thing is that family of sets is a set? It's only by replacement of the ordinal that's naming each one with the set itself. So you need the axiom of, that's exactly why the axiom of replacement is in set.
But what you are telling that?
Just that to get the cumulative hierarchy, you need replacement as well as
Exactly.
infinity.
I left out there.
To get past the finite cumulative hierarchy,
Yeah.
you have to.
But then,
I should try.
how you can say that the cumulative hierarchy give a model of ZFC? Because you construct the relativity, you need the SFC already. So that URGT is not a model of ZFC.
That's right. I think that's a real problem. Well, actually, I think that's kind of the content of Gödel's incompleteness theorem, in a certain sense.
Okay.
But anyway.
New depths that I didn't even know.
So several things. It seems here that he's only constructing the initial segments.
Yeah.
So if you want to construct the infinite, the set of natural numbers out of all these, or the infinite, the first omega, replacement is not you cannot use replacement either because you don't have omega. So you have to assume infinity first.
Oh yeah, that's true too. You need infinity and replacement. Yes.
Although I do cite that actually.
Yeah, but in any case, in here you're taking the union of the two
not the model of
precedents, right? Okay, so what would be V2?
If a model is a
Right, yeah, there's an
if a
awkwardness
model
if
means
we
you have
want.
a set.
About
Well, no, but if
axioms,
you take
yeah,
V2,
you have a set,
V2 is
you
a
have a model
union
of something.
of the set that contains the empty set union the empty set.
Yeah.
So V2 is equal to V1.
Then in which sense that they see?
Yeah, you have to keep the empty set as a distinct object.
But if you try with V3, this is not going to give you exactly that. This is going to, you see, because this is not the recursive definition. The recursive definition is Vi plus 1 is equal to Vi union the set that contains.
Oh,
Ah.
yeah. So you just
Okay.
mistyped.
You
the
mess up the
recursive
Yeah,
function.
that's
Well,
that's a typo. That's that,
But-
that's
I can't
but it's
remember if I
important.
may have meant to do it, just
Okay.
misunderstood, but.
Okay, but then you have to tell me how do you construct the set that contains that element?
Sorry, could you repeat that question?
Then I guess that this hierarchy, which by the way, this is not the cumulative hierarchy, this is the natural numbers. The cumulative hierarchy is the power set of the previous one.
Okay, well, yeah,
So
then
this
I'm
is-
out of my depth.
These are the natural numbers that you're
Yeah.
constructing.
Yeah, yeah.
Okay. But then the recursive formula would be Vi plus 1 is equal to Vi union
Yes.
another set. What set?
That's
The
right. yeah.
singleton of Vi. So I guess that you have to tell me from Vi, how do you construct the singleton of Vi?
Which is also what you started saying when you said that the problem is in V1.
You need a union.
From
That's another axiom, but clearly Ben wanted to construct a cumulative hierarchy here, so I think the recursive step should be the power set.
I think so. I think so too.
Okay.
So you add to your.
I tried with union and it didn't work. So, So
the
the-
power set, you need the power set axiom. You need a list of axioms.
I actually had a slide in here doing it with the power set, and I thought, oh, it worked just the same for union. The extra naive set theory is what I was doing, not just naive set theory. All right, so how far is it from the cumulative hierarchy? It's pretty far. Okay, it's that far, all right.
Here
fair
you're
enough.
constructing only one more element, and the cumulative hierarchy you're constructing 2 to the power elements.
Yeah.
So it is the difference is linear versus exponential.
But we should let him keep going because you were really only interested in getting expanding universes, which you're doing here.
Right, so we'll see whether the next,
Because that had to do with the converse Barkin formula.
yeah,
So the problem is just with the term cumulative hierarchy.
yeah.
No, I think that probably does actually want the cumulative hierarchy there, because
Well, let's see.
you probably
Yeah.
actually want a model of set F state,
Mhm.
as we know.
Well, I mean, Leitgeb sure does.
Yeah.
So the point I'm trying to make, it may not be so important, but would Leitgeb want, of course, he would want the full hierarchy.
Mhm.
So I haven't been able to help him as much, at least in this area, as I wanted to, but that's all right. I'll learn something in the process, and that's how it goes. So what I wanted to, supposing that had worked as planned, although at a certain point you do, I mean, if you take a union, you do get a bigger set, right? That's true. There's some growth. If you start out with any.
There's only non-proper growth,
Okay.
so, right, because if you union the same set for itself.
Okay, so if you have two distinct sets and.
So just greater than or equal to, no, that's
Alright.
greater than.
Okay, all right. Well, so we'll see how close this part was. The worry I had was, suppose we get the empty set and it exists necessarily. And suppose we are able to form some adequate growth. Whatever it is, cumulative hierarchy, we get that straightened out. Is that growth gonna preserve the necessity that we think we had with the empty set? And so I have two parts to this argument. I'm gonna say, well, we can always get more sets while preserving necessity, and there will be a unique result. It won't go out of control. So my very brief argument is because we've granted the necessity of identity way back. We're ended up granting the necessity of set membership with non, as I like to call it. Any names are involved. Let's say ordinals are functioning as names. We can take those as rigidly designating. with replacement, they can form a set. And we have, by steadfastness of the empty set, I didn't mean anything special, just that it necessarily exists, or we can get it in any world. The only worry I could see about losing the necessary constructibility of this growing collection is, well, the way I was using union in my mistake. My mistake at union, well, the way union is defined, it uses disjunction, and the box does not distribute over disjunction. Necessity doesn't distribute over disjunction. So maybe this could somehow interfere. We could lose necessity somehow. But my argument at this point is basically that there's going to be something there that's going to be a bigger set. We know for sure. That's guaranteed. So its identity may not be guaranteed, although it seems to me that with union, there is a unique output. So we can determine identity from the identities of the inputs. But all that we mean by union is that there's going to be a set and it's going to have members, and it's going to be bigger if you have two distinct sets that you're. And then by a dilemma argument, you could say, well, X belongs to A or X belongs to B. The consequent of each of those conditionals is the union of A and B. Does that make sense to you? Mm-hmm. Okay. I'll take that for now. One success. Link to these things, yeah. All right. So I might not have gotten as much out of this checklist as I want, but I was feeling bold when I wrote this slide. So I'm claiming that we got the 3 desiderata, and the reminder of the desiderata are at least a set that exists in every world, and indeed a hierarchy of sets, a growing hierarchy of sets. They can be constructed the same way in every world. So there's no reason why this couldn't be done in our little spaceship that goes to any possible world. As long as we have life support, we can keep going. And then granting replacements, we can use ordinals. There's the rank or stage of the growth that you're at can be used to identify that set across worlds. So you got to grow a hierarchy in one world, like a chia pet, and a hierarchy in another world. Well, how do we know that they're not? You could mismatch them. You could get the wrong levels matched up, and that's not good. Well, if they're indexed ordinally, then we can identify the ordinals. So it seems to me that what I've done so far, defective as it is, perhaps with some repairs, could be helpful to Leitgeb. I'm not going to go so far as to, I have a few more sort of wrap-up discussion slides, go so far as to say, this is how you get all the theorems of ZFC. I'll have to leave for another occasion also. Here's what I want to do is take a particular theorem and its axioms, and let me do the translation into set theory. Let me use the cumulative hierarchy.
Okay.
Details that Leitgeb, some other details like that. So taking a big deep breath and a big step back, we're all going to make it, I promise. To understand why did I undertake this with all its travails? Because to understand mathematical, it just struck me reading his article. There was something right about the approach. I think something right about the approach was we want to, in a sense, it's history. Where does the necessity come from? How can we explain why math has this necessity? Well, if we can find a source and we can find the channel, then we know how the water gets into the house, so to speak. Where math is the house and water is necessity. So to reprise some of what at least I take to be the advantages, we kind of get around this internal-external explanation dilemma that I set up, which is really modeled on Benacerev's access dilemma, to just put that out there. But we might be able to swap out other foundational areas, but that's a topic for discussion because people may have some thoughts about that. I think that derivations can be explanatory, at least they can set up a framework within which we can test out potential explanations. And if we do find another source, it could be that there could be more than one. It doesn't have to just be one, it could be distributed, so to speak. So to reprise some of the costs or barriers, the conditional necessity gap I found, which was we didn't really get the necessity of the schematic theorem. We had to bring along with it some axioms. So we had to basically import a proof from axioms of a subject area with the theorem that we wanted to trace. So we didn't get as strong a result as we wanted. And then it turns out it's not just that I couldn't derive the necessity of membership. There may be some other, well, I look forward to repairing the rest of that. Necessitating the axiom of extensionality. So what options are we left with? I look forward to hearing from all of you, but a few which I see are, there may be some way to necessitate the axioms. And if we could do that, then Leitgeb would get his unconditional results very easily. We basically discharge the antecedents of these axioms. We can necessitate them. Or we could just accept that it's okay, we don't need to discharge that antecedent, that assumption of importing the axioms from areas of math. If we are convinced by if-thenism, there's no problem to begin with. Alternatively, we could find a source other than the axioms. So what would that be? It might not be even an area of mathematics. It might have nothing to do with axioms. It could have something to do with, in logic, we often explain logical necessity in terms of logical form. It's quite unlikely, but if we were to discover something called mathematical form, or which answer to that description, which somehow, this sounds very far-fetched, but we're doing philosophy, so what? See, if you have a little freedom, you got to use it. If we found that, maybe that somehow could explain the necessity of that. Or we could take the ingredients that we have, and if we find, replace CFC perhaps with another foundational area, we could grant ourselves, I think, identity wherever we go, whatever source we try to get necessity from. We probably will have identity in some form. And in type theory, more than one form of identity, if I understand correctly. Sure. Joke. He's a nice guy. I like him. So, for example, in arithmetic, that Frege's little trick about the non-self identity, that's how he got the number 0. It wasn't to form a set, it was the number of objects that satisfy the formula. It is not the case that X is self-identical is 0, because there are no objects, because it's necessarily false. Every object is self-identical, no object is not self-identical. So maybe we could find just patterns like that in different areas of math and use that to get some object, which we could build on top of. That's part of the motivation behind abstractionism. But that's the end. Okay. So thank you very much for your attention.
Okay, I am chair, so I cannot read them. Okay.
So my question is very naive because I'm not used. I don't know enough philosophy to and even less about necessity. I think I see a danger in this pursuit of necessity in set theory. Somehow it suggests to me that arguing in this direction, you will be able to get to the fact, you will be able to get to the point that you can prove that if there is a model of set theory, then there is only one model, because set theory is necessary. And if you prove that, then you're wrong. This cannot be proven,
No.
because if there is one model, then...
But there is a model that ZFC, it's not a theorem ZFC. It's a meta-theorem on ZFC, so it's not applied. There is a model of ZFC.
If there is a model, then there is only one model. Why? Because of the necessity of things, I don't know.
Because you're thinking of the cumulative hierarchy as this unique structure that would be the one and only model.
Yeah, if you prove that the cumulative hierarchy is exactly the same always, then somehow it is suggesting to me that you can only construct one model of set theory. Maybe I'm completely wrong. It's something that might worry me if I do this project. But that's only my only concern.
No, it's a good one. I mean, one answer could be, well, let's think about other models that do the same job that I was trying to get out of the, what turned out not to be the hierarchy.
Yeah.
Was John, I think.
Okay.
And so,
Eric has
order. John,
That's true.
Eric, and sorry,
Ainsley.
Ansley, and Peter. Okay, this order.
So you're worried about, one thing you're worrying about is the conditional aspect of it with the translation,
Yeah.
right? And maybe this is just what the observation from Marco was, but it seems like to even have a translation, you have to build in the axiom. Like you'd have a conception of translation where axioms weren't involved. Like, so if you're gonna, like with translating a theorem about group theory, presumably you would encode the group operation as triples, right?
Yeah.
But the triples have to satisfy certain axioms for it to even be a group.
Yeah.
So I don't even know how you have a conception of translation without building in defining axiom.
Yeah. There was one little thing that I skipped over, which is there's a corresponding for every operator in the origin in the whatever group theory. There's a corresponding operator in ZFC, I'm stipulating, but with possibly a different arity. It was a 10-page paper. This is a point he did not really address. And so that was just one small attempt I made to say, well, that's a good question. We may have to make some adjustments. What are the details of this translation? And I really need to work through a specific example.
Well, yeah, well, it seems like it's just that to even have translations from, I mean, numbers are different because there's aspects of set theory that give you
that correspond so closely,
the numeric structure. But with things like groups, you need, I think it has to be built into the translation.
That's a good point.
Eric.
I want to address the issue of another source or another framework for it. And maybe I kept wondering if instead of using set theory here, you use second order logic, let's say, what would happen? What would correspond to the things you were talking about? So as for second order logic with identity, I guess.
Yeah.
So yeah, if the same argument, you need a logical notion of object, then you get identity.
Yeah.
What would correspond to the element roots that's necessary? Maybe something like a logical notion of concept. Now suppose you grant that those two things and you work with the if-then-is version.
Yeah.
Would you get everything you want, or would you still need some existential things like with the empty set and so on to go through? So what would correspond if you're working second order logic to that whole discussion about the empty set and using the hierarchy?
Yeah. So there are really a number of very good points in there. One is, well, maybe we just don't need.
Let me add one more thing. Apart from that last point about existence, so if it started to look to me like you're getting if you do it especially along those lines, you're getting the necessity of mathematics out of logic. You're basically arguing, you're almost arguing that the necessity is logical necessity.
Yeah.
Insofar as set theory is very close to
But
second order
you
logic.
need to accept the first action for second order logic. Now, second order logic is very powerful, but are you ready to accept that for any mathematical theory, you are a translation of this mathematical theory in second order logic?
Right, you get a parallel question there.
Sorry?
That seems a parallel question to what you.
Yeah, first premise. First premise is necessary.
Yeah, and it seems to me more plausible for second order logic than set theory, actually.
So here you have to make a statement of second order logic.
Right.
Yes.
So you are ready to accept that? No, sorry.
Translated into set.
Into set theory, yeah. That seems to me more plausible than for set theory.
Yes.
That doesn't mean that it's unproblematic, but it seems more plausible than for set theory.
That step, but then the necessity of SOL.
Right.
Is
right.
You've moved the problem.
Right.
Yeah, but I think it's a better place to.
Yeah, maybe.
For necessity, yeah. Closer to first order logic, I guess. And most people would grant the necessity of that.
But you would need modeling first of all, logic.
Oh, certainly, yeah.
To get mathematics.
And I mean, off the top of my head, I'm not sure. I don't know.
Okay. Now there's
SOLs enough.
That opens a different can of worms though, because now if your M is a statement of some part of mathematics that's not finitely axiomatizable,
right?
Or even say not recursively, maybe it's recursively enumerably, but not recursively. Then you're going to run into compactness problems with this translation, with second order logic.
Axiomatization
is
a word.
So that opens up another problem. But even in this, do we know that Box distributes over infinitary conjunctions of things? So if that's a theory instead of just a formula,
yeah,
which you need, right? Your version needs that phi m is not just a statement of a theorem.
Not a theory.
No. Phi m is a statement of that says in a model in group theory this holds.
Yes.
Well, if group theory is not a good example, but some example that's not finitely axiomatizable. How do I know that the box behaves correctly in this situation?
You mean that if
that's an infinite conjunction of formulas,
Fm it become equal to X.
Yeah, exactly. Yeah.
It's not a finite
Yeah.
statement.
How do we know that the necessitation behaves correctly in that situation? Because those aren't even formulas then.
There is a lot of things under the rug of this translation.
Exactly.
Because there is nothing said about how you do the translation.
Or very little. There's an injection.
Very little. Right.
Yeah, so funnily mine is one way of answering it was certainly to go in Eric's direction. But okay, so it seems like here we're deriving mathematical necessity from metaphysical necessity. But it seems plausible to think that mathematical necessity is stronger than metaphysical necessity, right? It's between logical and metaphysical. And so I guess one way to do it is like, so doesn't that mean that you just haven't proven the thing that we actually want, right? Which is the notion of like genuinely mathematical necessity.
Yeah.
Or, why does it suffice to rely on metaphysical necessity?
Yeah, so, okay.
And again, obviously, not your own project, but yeah.
Yeah, but I mean, if I could do something with it, that'd be nice. And so, I mean, Leitgeb calls it metaphysical necessity and says true in all possible worlds, and that's called a day. So another reason you think that he's working with metaphysical necessity is because we're basing all this on the necessity of identity.
Yeah.
And that's usually how there's another way to characterize metaphysical necessity.
Yeah, so I guess I'm saying, why should I think that, like, so metaphysical necessity doesn't give me logical necessity, right?
Yeah.
And so even just, do you personally think that metaphysical necessity is stronger than metaphysical necessity, or are they the same?
Yeah. Right. So yeah, is mathematical necessity at a really in-kind different level from metaphysical necessity?
Yeah.
And perhaps in-kind beneath logical necessity.
Well, it's definitely that.
Yeah,
somewhere
I
in
would say
between.
post
In between.
logicism's demise.
Yeah, there are still some people who are trying to make it work, but I agree with you personally. My own view is that it's between the two. And I mean, one quick thing you could say about it in this instance is, in general, when considering whether a statement is metaphysically necessarily true, we can't construct a necessarily existing object. We can't like construct the empty set or have an axiom that guarantees a necessarily existing object. At least that's not often, from what I understand, that's not often done in a discussion of metaphysical necessity. So the setting of math is different. You can do things, you can kind of create objects in a way which is different in kind from any other setting. except possibly logical. And so there's something about the content, I would say, that gives extra, bumps it up from sort of garden variety metaphysical necessity to taking the elevator up to the penthouse. That's the best thing.
I'm curious because in philosophy, and this, you mentioned at the end that logic is something different from mathematics. I mean, to me, it's usually like a sub-discipline, but
for you, yeah,
it's different. What about the necessity of logic? Have people looked into that? Is that a topic in philosophy?
Sure, certainly it is. I would say 99% of philosophers would just accept that logic is necessary. You know, the truths of logic are necessarily true. The contradictions are necessarily false.
Yes,
and
I'm not part of this philosophy.
Yeah, well, I said 99%. Yeah,
not speaking for me. Huh?
Make some allowance here.
I'm just curious how you would try and prove it, because
there's this famous paper of Hilary Putnam's who said, no, it's an experimental science.
Logic.
Yeah.
Mm-hmm.
Yeah.
Logic is experimental.
Because of the quantum mechanical situation where the lattices that you come up with are modular and not distributed. And it's this von Neumann-Berkhoff paper, but then he riffed on that and said that suggests that logic is an empirical science.
I'm trying to remember the title of that paper.
Yeah.
But in the tradition of Quine and the pragmatists, there's a web of belief. And you have to push perhaps harder on logic to change it than anything else, but you can change your logical beliefs.
Yeah, so that's kind of, I would say there's not a lot of research in it because the researching logical necessity is just researching logic. Which, and so obviously there are people that do that, but.
Logic is sort of maximally applicable to statements. And what carries the weight is just logical forms. You have like so little, I guess. No, I'm sorry. Yeah, I don't have a good answer for you. Short answer.
So I have myself 2 points.
Yeah.
First one, these are the 2 first premises. Okay.
Mm-hmm.
My problem is the following: if you accept this premise, we are saying that it's necessary that there is an equivalence between a mathematical statement and the state of ZFC.
Yeah.
And then you accept that in ZFC it's true, then it's necessary true.
Yeah.
But if you replace, then because of that, replace M here. So in fact, you are supposing what you have to prove. You are in fact supposing what you have to prove.
Mm-hmm.
Because what you have to prove in the end of the story is that this is what you have to prove. But this is already the 2 premises.
Yeah, it's not a
So
different
you have to
derivation.
suppose what you have to prove.
But he gives the derivation there. I mean, you have to do some more work to get box phi m from those
No,
something.
I not want to say that you derive this directly from that. But I to say that morally, what you want to prove is already there.
Yes.
Yes.
Isn't it
That's
true
why
of
this
all
proof.
theorems?
Sorry?
Is it not true for all theorems that what you have to prove is already there, because otherwise?
It wouldn't be.
No, but it's there in the
That's inductive
assumptions.
logic.
No, because these are not so.
This is circular. This little circle right here.
I want to say that in
Yeah.
fact, what you are supposing is quite strong, because what you are supposing is that some theory is necessary, and mathematics is the same thing that some theory.
Yes.
And so, of course, if the theory is necessary, mathematics is the same thing that's necessary. It's a theory, mathematics is necessary.
Okay, so no.
From the
one's
end of the
saying
story.
what Hannes is selling.
So, this is my first
I
point.
did a bad job, man. I screwed that job.
I think your argument works if you erase the box in number 1.
My argument?
Works even if you erase the box in number 1, because if the 2 statements are equivalent, can't you just substitute?
Yes, of course.
Yeah, so you
Even
don't need
if I eliminate that, of course, of course.
Yeah, this is.
But second point.
Well, that's actually important.
Sorry?
That's actually important.
Oh, yeah, 'cause-
For Leitgeb.
What?
That you don't need the box in premise 1.
Yes, you need a certain moment in box one because of 6.
Not in my life.
No. What you need in box
No, yeah, you can see that one never. Oh,
7.
it's from 4.
7 required in box in grade 1. 7 required in box.
So you hypothetical syllogism from 2 to 8.
But I think there's something, what is interesting about it, I did discuss this previously, right? So this principle number 2 essentially means that you have no possible words.
Yeah, that's what
Right, so it's classical propositional logic. And that makes a lot of sense because he already kind of says epsilon and so membership and equality are rigid. So yes, there are no possible words. Right. And this proof is so simple because it doesn't actually really use modal logic. And I think that was also the point that you wanted to make, Peter.
Right. Okay, then I have a second point that is the following. So even take only 2. 2, is not only a question whether to know whether it is plausible or not. Also, I do not well understand what does it mean. Because what does it mean? This. It means that it is a theorem of ZFC. When I can take it. But modus ponens, I take it, I have this. Okay? So, this is modus ponens.
It means that if...
But what is this premise? This premise is acceptable when this is the theorem of ZFC. Correct? Okay, so now I take an axiom of ZFC, the axiom of infinity. Of course, if the axiom of infinity is a theorem of ZFC.
Yeah.
And so I have that, I have the axiom of infinity, and so now I conclude that in any possible world there is an infinity of objects. It's necessary to have an infinite object in any possible world. So a world made by only finite objects is not necessary. It's not possible.
Many pure sets.
Pure sets, they're pure sets, it's not.
Concrete objects, and that's why.
I think that's
No concrete object. So we are right.
Yes, I
What
think
we
you're,
are writing
I think
here.
you're right, and that is what it says.
So there is no possible world
in which
with
there
only finite objects.
in which there are only finitely many pure sets.
And hence objects.
So it's not implausible? Is not a direction of the sort of 2? Take the axiom of infinity.
Well, I don't even know what it means to be
I mean, take the axiom
set
of infinity.
in a world. So
And then I conclude that the axiom of infinity is true in any possible world.
Yeah.
Yes, we accept that the axiom of infinity is true in any possible world.
Well, but, I mean, yes, that's
Yeah.
what people say when they say that mathematics is necessary. Is it bad and for them to have said that?
No.
Lots of them say that.
If you accept. According to me, it is a reduction to absurd of the thesis that mathematics is necessary.
Yeah, I know.
I reject completely the idea that mathematics is necessary. And according to me, this is a reduction to absurd.
Yeah, but, Conant, Lewis.
No, there are a lot of people. I know. Because it seemed to me obvious to suppose that if necessity possible means something, it should be possible to have a world where there is only a finite number of objects.
So it's not the axiom itself. Having an infinity in some world is okay, but there should be one world at least where there's no infinity.
No, I do not deny that could be possible world where there is an infinite of set. Okay, but I would like to assert that there is a possible world in which there is only one object.
Yeah.
Or the object.
Yeah. Should be required.
Or a finite number of objects.
But I think
in that world you cannot do mathematics, right?
Sorry?
In that world you cannot do mathematics.
Here, mathematics is not
So it's not necessary.
There is no question of mathematics here.
That's what he said.
Forget mathematics. There is only set theory here.
Yeah, but then in a world with no sets, there is no set theory.
So forget mathematics. You have simply this action of infinity is necessary. So action is true in any possible world.
Mhm.
Seems strange. It seems strange to me.
But it's the kind of objects that you have. Those are conceptual objects. Those are sets that are formed out of sets at the end ending with empty set. What is that? Which kind of object is that? That's not a chair. That's not a common object. It's something in your mind. So why not? There are infinite why not? If I accept one, why cannot
Yeah,
I
they're
accept all of
very
them?
cheap, you know.
Thoughts of my thoughts of my thoughts of my thoughts.
Why? So that's a.
So to me, thinking of a world in which there are only finitely many atoms,
No.
that's one thing.
First of all, I do not see where is mathematics here. There is only set theory.
Mm-hmm.
So
Yeah.
in this world, you cannot make mathematics. Okay, you cannot make mathematics. That's not my problem. My problem is that you are supposing this, you take the axiom of infinity, you conclude that there are only possible infinite worlds. I don't see the fact that you cannot mathematics what is relevant. But even you can perfectly accept the idea that you have something that is a theory of natural number where there is only 100 natural number. And in fact, our usual life, we do not use very often natural number more than 100. So now I take a theory, arithmetic, that is exactly as arithmetic, simply that 100 is the last number. It's a coherent theory. What is the problem of this theory? Where is the problem of this theory? It's a perfectly possible theory.
Consistent.
Consistent.
So what's the problem? Yeah.
And very useful, by the way.
Right.
So what is the problem?
Yeah. So you're rejecting 2. That's fine.
I reject 2. I say I reject 2, I reject all the argument.
Yeah, sure.
The heart of the argument, yeah.
I was
That's what you-
like, I think he also rejects one, so.
But this is another story. No, I also reject 1.
Yeah.
But I say it's enough to reject 2 to reject the argument. That is my point.
Certainly the conclusion does
I
not
find
follow
one
that.
also good.
Yeah.
Why he rejects.
But this is very helpful what you've done because it sort of focuses what the problems are with this.
Oh, no,
Like you said,
it
you're
is not a
talking about the
criticism
cost
to
of
ban.
this argument.
Absolutely.
Yeah.
Oh, good, I'm glad to hear it.
No, this is what you did is very good.
And in fact, we kind of identified where these problems are now, I think, in ways.
It's one thing that appealed to me about the
Yeah.
article.
Yeah.
So one question I still have about one, which sounds stupid, but like, I mean, we don't really know that phi m and phi z are in the same language, right? So we don't even know that the biconditional can be written, or do we?
Right.
No, that you take the two languages together, you construct the language by unification of the languages.
So,
That's
Is
not as
that
easy
what
as you think it
is
is.
that what, that's not what how I understood that. Okay, so then I need to.
That's the problem.
I thought this was in set of C, the biconditional.
I think this is. I think
No,
this is
no,
natural.
no,
Natural
no. I
language.
think that this
Yeah, but in natural language,
is
you
the
don't have-
conditional is in the language that result by putting together the language of ZFC and the language of mathematics.
Okay, so this is just a symbolic notation for a natural language connected.
I think.
But then
Or a
maybe you
meta
should
language.
use different notation because like sometimes you actually mean formulas, like when you discuss
Right.
extensionality.
This is
So that could be,
They're much more cares.
yeah.
Sorry, I don't understand why it can't, because I don't understand why it can't be a logical derivation in, is it S4?
Okay.
Okay, sure. With the language being the union of the two languages.
You have the union of the two languages. You're allowed to do membership between things of the two languages, between formulas that are. If you put the two languages together, you mixed all the formulas. So
No, but you can still identify which ones are phi m formulas, and if you just assume that phi m only one.
it's not that. It's that you get a logic in which all the you can construct formulas that are completely.
Yes, but
meaningless.
those formulas will not occur in.
It doesn't matter that they not occur, but they are going to intervene in the consequence of the logic. They are going to intervene in the derivations. So there are meaningless things that are going to intervene in your derivation.
But
You don't want that.
but but do they make them false?
It's possible. Mixing logic is something.
I know it's very difficult. I know it's very difficult. My advisor works on theoretical equivalence.
Yeah.
So, but
What's your question?
Okay.
typing methods.
I think that this was the longest seminar of the.
So far, yeah.
Oh, you want, yes.
Not infinite though.
So,
that's
but you,
Kept it finite.
you have to admit that the pupil here is improving the master. Because 4 hours and a half. Thank you. Very good. Thank you.